As always, practice makes permanent. Engaging in some form of retrieval practice, especially at spaced intervals, is one of the best ways to convert your new learning into long-term memory. So here are 3 problems related to this chapter. We're going to practice. It just says complete and balance, if necessary, each of the following reactions. So one of the first things I like to do when I'm approaching a problem like this is just identify what kind of organic families I'm working with. So I see a carbonyl group right here. So I often like to, when I locate a carbonyl group, look at what it's attached to on either side. And since I have a carbonyl group that's attached directly to a nitrogen, I know that this is an amide. So I have an amide and water, right? And then I recognize sodium hydroxide here as a base. This helps me identify what I'm supposed to do here because I know that amides can be hydrolyzed, so that means to break with water, under acidic or basic conditions. So I have a better idea now of what I should be doing. I'm going to break this amide under acidic conditions. So when an amide breaks, we're going to locate the amide linkage and break it there. So I'm going to generate the carboxylate portion. So I want to walk you through kind of how I think of this, even though this might not be necessarily the most accurate mechanism. This isn't necessarily how it reacts, but I like to just think about breaking the amide into its 2 components and then going back and considering the basic situation. So if I'm going to break an amide, I'm going to generate the carboxylic acid from whence it may have been derived, or, I'm going to create a carboxylic acid from that. And then I'm going to create an amine. And so if we want to think, how does this happen? Why does this happen? Remember that we can view water this way. It's hydrogen bonded to a hydroxyl group. The hydroxyl group is going to come over and bound to my carbonyl group, and that's how I'm going to generate my carboxylic acid. My hydrogen is going to come over and come here and bond here, so I'm going to get then NH. I should go up a hydrogen, so NH3, so this is ammonia. So I'm not generating an amine in this case, I'm generating that inorganic ammonia molecule, so I should from the hydrogen. Now that I've identified my 2 products, now I want to think about, but this is under basic conditions. So am I going to get a carboxylic acid, and am I going to get an amine from that? Or an ammonia? Well, not in a basic situation. So remember, this is an acid. This is a carboxylic acid right now. And so a carboxylic, any acid in a basic environment is going to be neutralized. So there's all of these OH minuses. I apologize for the dogs. Just ignore them. Someone must have knocked. There's all these OH minuses floating around from my sodium hydroxide, which means they're going to pull off this hydrogen. Remember, a carboxylic acid is acidic, so it's going to lose this hydrogen. It's going to get donated. And so rather than creating, rather than creating a carboxylic acid, I'm actually going to create a carboxylate ion, which, I like to either circle that charge to really identify it, or I like to put brackets around it and put the charge on the outside. Now, because I have this negatively charged particle, I would expect it to be attracted to the cation of my base. So I have created here a carboxylate salt and ammonia from which is what we would expect to create, ammonia or an amine and a carboxylate salt, from the base catalyzed hydrolysis of an amide. Looking at the second one, I go to identify this, and you might be going like, is it a carboxylic acid? Is it an ester? Oh, this weird symmetry of carboxylism around this oxygen tells me that this is an acid anhydride. It's like 2 carboxylic acids bound together through the removal of water, which is what anhydride means. And this is ammonia. So when I look back, I've studied some flashcards or reaction maps or some concept maps, and I remember that an acid anhydride can react with ammonia to make an amide. So this problem here, this was about amide hydrolysis. Let's even put that there. This was amide hydrolysis. This question is about amide synthesis or preparation. I like synthesis, it sounds fancier. Amide synthesis. So when I create an amide, one thing I remember is that I need 2 molar ratios of ammonia. And remember it said balance if necessary? That's because I'm actually going to need 2 molar ratios of my nitrogen containing compound. One of them is going to go to generate my amide. So I'm going to break this acid anhydride here, and I'm going to create my amide structure, CH3, bound to a carbon, get my carbonyl group, and then I'm going to bind it to the nitrogen. And the nitrogen, you'll remember, one of the nitrogens loses a hydrogen. So I'm going to have 1 hydrogen less in my amide. And then my other nitrogen is the one that gains that. So I know I'm going to make, I'm just going to do NH4 rather than do it structurally. So I'm going to make that ammonium. Let's do brackets this time. I'm going to make that ammonium ion. And then I also am going to have this left over. I'm going to have this, and it kept this electron. So it's an ion as well. So I'm going to make this acetate ion from the remainder of my acid anhydride. So using brackets. We often will list the anion first in organic chemistry, which is funny because we don't in inorganic. So this is my salt that gets generated from my amide synthesis. So I needed 2 molar ratios, 1 nitrogen containing compound. One of those went to making my amine. I want you to notice it's down a hydrogen to make room so that it can bond. But that hydrogen had to go somewhere, and where did it go? It protonated the other ammonia, and that's where I end up with the ammonium salt. So then down here, what do I have? What do I have going on here? I recognize this organic family as an amide. See the amide linkage? See the amide functional group right here? So I have an amide, and again, I'm reacting it with water, except this time in the presence of an acid and heat. So you want to make sure you have a general idea of what acids are. This could also be written as H+. It could be other kinds of acids, such as sulfuric acid or, hydrogen. There's almost, nitric acid. So to me, then I'm like, okay, what am I looking at here? I'm looking at amide hydrolysis again. I'm breaking an amide, but this time it's acid catalyzed. Now I still actually like to approach it the same way as I showed you before. Rather than focus on, okay, when it's acid hydrolyzed, what are my products? Which one's in the salt form and which one's not? What I like to do is just kind of go back to what I did before, is just go, okay, let's create the 2 structures. So I'm adding water. Oh, I want to do H bonded to OH so that I can see that I'm going to break here at the amide linkage. Right? And I'm going to generate the carboxylic acid from that because I'm going to replace, there's my carboxylic acid, and then I'm going to create that ammonia molecule right there. So I make my carboxylic acid and my ammonia. Now that I've done that and I've generated those 2 structures, then I like to think, but wait a minute, I'm in an acidic environment. There's acids around here, so there's H pluses all over the place. So what is that going to mean for my products here? Well, that's not going to impact this, because this H plus isn't going to pull off this hydrogen of my acid. When an acidic molecule is in an acidic environment, it doesn't deprotonate. It keeps the proton instead. So I'm going to keep this. This is one of my main products. I make a carboxylic acid. So in an acid environment, my acid is in normal neutral form. In an acidic environment, my acid is in my normal neutral form. However, remember that these nitrogen-containing compounds like ammonia and amines, they're basic. What do bases do in an acidic environment? They get neutralized. They act as bases. So all of these hydrogens around, they're going to bond to that lone pair here. So instead of a 3, I'm going to put a 4, and that, of course, makes it charged. So I end up with my ammonium ion, which would be attracted to my chloride ion. And so you can see here that I made an ammonium chloride. In fact, I specifically did make ammonium chloride from this reaction. So a pattern I want you to notice in these problems, particularly the amide hydrolysis problems, whether they're acid, is when you're in a basic situation, in a basic environment for amide hydrolysis, the base, because ammonia can act as a base, stays in its neutral form. Base, base. When you're in an acidic environment, the acid product stays in its. So I find that to be a helpful memory tip. Which one is going to end up creating the salt? Which one's going to not? It's going to depend on that environment. In a base, the base stays normal, if that's good language for you, and the acid becomes the salt. In an acidic environment, the acid stays normal and the base becomes the salt. And the last thing I want to share with you is an amine reaction map. And I love concept maps and reaction maps. I think they're so critical for organic chemistry to help your brain see the relationships and also the differences in these different products. So here we have amines. So remember, amines are organic versions of ammonia. So they're a nitrogen bound to at least one alkyl group, and then the remainder could be hydrogens depending on their classification, or they could also be alkyl groups. So an amine can become an amide in 2 different ways. It can become an amide by reacting with an acid chloride, or it could become an amide by reacting with an acid anhydride. We see their structure, its general structure like this, and then whatever those R's are. And either way, you get an amide. Your other product is going to depend on what you react it with. If you react an amine with a strong acid such as HCl, really just any strong acid, you are going to get a salt, and it's going to be an alkyl ammonium salt. Alkyl ammonium. So NH3R, and then it's plus, and then whatever the minus is going to depend on what your acid was. Amines even just react with water, though, because they're weak bases. So when you react an amine with water, it accepts a proton from the water, and you get an ammonium ion or an alkyl ammonium ion, and then we're generating hydroxide. So you got your R and your N, and then these end up being all filled up with at least one hydrogen and a positive charge, and then the water then, so water, that hydrogen came from the water, and we're also going to get the leftover OH, this hydroxide ion, and that's what impacts the pH of a solution. As that concentration goes up, the pH goes up beyond 7. So I like reaction maps where we can almost look at a whole chapter or a whole portion of a chapter pictorially in one place. And I'd encourage you to develop your own.